It certainly doesn't cost anything to record it. So, would you hit the door, please?
Hello, you.
Okay. So we've got a circuit that nobody in their right minds would ever build.
Yeah.
And I will say this about circuits in this particular book. My observation is that they are interesting problems,
Was never happening.
but they would never happen in real life.
It's just to make you think.
Yeah. Okay. Now this symbol down here at the bottom just says that that point is grounded, and that simply means that this point is at 0 volts. So we're going to measure all our voltages relative to that. Okay. Now the delightful thing about this circuit right here is that it has one loop, and because it has one loop, it has exactly one current going through all of this thing. Think about that for just a second. That has to be the case because there is nowhere for this current to go except through ground. Yes?
Okay. So is this where you like add and subtract the battery voltages?
No.
And then
Sure. So I have just one current here. And now I'm going to use Kirchoff's law, and I'm going to go around my circuit like so. And I'm going to say that the sum of voltages as I go around loop number 1 adds up to 0. Well, that's fairly straightforward. Let's do the power supply first. We're going to start here. Well, since we said it, we'll start here. For this power supply, am I going, as I walk this way, am I going from plus to minus or minus to plus?
plus
I'm going from plus to minus. Therefore, I'm going to treat that as a voltage drop. I'm going from plus to minus. I'm losing voltage. All right. Now let's keep on going. Here we get to a resistor, and the resistor has this current I going through it. Which way does current always flow? From positive to negative. So that means I can mentally or physically mark up my resistor plus and minus just like that. So my resistor voltage is also going to be treated as negative. Negative how much? Negative V equals IR, 1,000 times I. Keep on going. My I is going this way, so this resistor is again plus there, minus there. And so I'm going to treat my voltage drop as negative across the resistor, minus 1,500 times I. And it changes. And it changes because now I hit this power supply, and how am I going as I walk this way? Minus to plus, so
which
I'm
means you
increasing
subtract.
minus to plus. I treat that as a plus.
Okay.
I mean, fine.
Så kan man inte göra en sak.
Yes, I do.
I'm thinking it's, you know,
Okay. Now, how about the 500 here? The five, why is it plus?
Right, no, I mean, mine always goes
Why is it
down.
minus?
plus
Towards the
The current is going this way, and therefore plus and minus. I'm going to lose 500 out. Now I come to this power supply. I'm going around the loop here. I'm going
Plus 20,
plus 20. That's right.
and then minus 2,000.
And finally minus 2,000 I. And all of that adds up to 0. Well, I look at this, and oh, happy day. I have exactly one equation with exactly one variable.
So all the variables are the same. All of them are signs.
Yeah. All currents. Do not throw resistors are exactly
So-
the same.
wouldn't that be like the I equals 0.003 amps?
Probably. That sounds about the right size.
Would it be okay if you like added and subtracted all the batteries and then like made it into one of a 5,000 resistor or ohm resistor?
It's exactly what I'm going to do, because I've got all of my constant terms here that are the batteries. Minus 30 plus 25 plus 20 is plus 15. And I have minus 1,000 minus 1,500 is minus 2,500, minus 3,000 minus 5,000. I is equal to 0.
So could I just do that instead of doing all the other things? Kind of like simplifying it, like we did before.
That's just what I did.
Well, yeah, I meant like this way, like with the diagram.
Oh, could you simplify it in the
Like that.
diagram?
Yeah.
As long as you do it correctly, that'd be okay. It works because we have a single loop.
Yeah.
For the others, it doesn't. And so then I get I is equal to 0.003 amps, just like that. Now we want to make sure that we are answering the right question here. I found the current, that's part A. Now they want the potential of wire A relative to ground, and the voltage drop across the 1,500 ohm resistor. So I want to take a moment to show you how to check your work once you're done. Your circuits are self-checking. And what I mean by that is that once I have my currents, I should be able to plug in and find the voltages at various points and get a self-consistent circuit. If I don't, I've made a mistake somewhere. So let's see how that works. This point is at 0 volts because they tell me so. And that means that as I go from here to here, this point will be at 20 volts because I'm going up 20. Now, as I go here, my voltage is going to drop. Drop by how much? Drop by 2,000 times my current of 0.003. In your head, what's 2,000 times 0.003? 6. That's right. So I'm going to drop by 6 volts. I'm going to go from 20 down to 14. Everybody with me so far?
And then don't you drop even further?
Yes. Now something strange happens. 14 minus 30 gets me to negative 16 volts. Yikes. Does that mean I messed up? Not at all. Voltages can go below 0 just like elevations can go below sea level.
So 0 is relative.
And it's going to go lower still because I have another 1,000 times 0.003 is another negative 3 volt drop right there. Or a 3 volt drop, I should say. And we're going to keep on dropping.
Well, isn't that all it asked for though? Was up to 1K?
Yeah. Yeah, but I'm checking the circuit here.
Another 5 volts.
And another, let's see, 1,500 times 0.003 would be 4.5. Yeah. So that would put me to negative 23.5 volts, right? But now relief comes because I go up by 25, and that puts me at plus 1.5 volts right there. And then finally, I drop by 500 times 0.003, which is minus 1.5, right? And that puts me back to 0, and look at that. When I come back around, I'm at 0 again. My circuit is consistent. Does everybody see how the checking goes? No?
Yes.
Yes. Okay. I got this.
Could you throw a bigger one the other way to check it?
Certainly. If I go around the other way, what happens is I start here, and now I go up by 1.5, and I get 1.5 again.
Then not like 5.
And then I go down by 25. Yeah. Okay. Questions? Comments or jokes? Excellent. Okay. Number 25, they give us a strange circuit. Again, one that I don't think would happen in real life.
I don't understand why it would.
Well, I've seen strange things.
What's the weirdest circuit you've seen?
A cube of resistors with diagonals. Actually, I've seen infinite, I mean, I haven't seen it, but I've seen problems that made reference to infinite networks of resistors.
What's been infinite resistors?
Oh, how many ohms?
like one here, two, and you had to find the equivalent resistance.
That's
The infinite network resistance.
Well, it was between any 2 points, kind of a thing.
Okay, that's a little bit better than. What is this? It's a total resistance in an infinite resistance.
Well, see, it's not as obvious a question as you might think, because if an infinite number of resistors in parallel, the effective resistance is actually 0. And if they're in series, the effective resistance is infinity. And if some are series and some are parallel, it could be in
between 0 and infinity.
Zero and infinity.
between. Alright, let's leave that alone.
Where do you put the batteries? Like I put it, yeah.
Where do they tell you to, which is between points A and B. And what they want us to show is that the equivalent resistance between R, A, and B is this awful expression 27/17 ohms.
You.
Sure, if you say so. So let's see how that would work out. What we're going to do is we're going to hook up a battery, and I am going to hook up a battery that is 10 volts because 10 is a friendly number.
Could you not just put the battery within the, like, in front of the, like, point A in the first resistor? Could you put a battery there?
I mean, like here,
Yes. No.
you could do it like that, but because
With that.
they told me to connect a battery across the points A and B, I'm going to follow the directions that they gave me.
Okay. I didn't understand what that meant across.
Well, do you see it here? Yep. Okay. Yep. And now what I'm going to do is I'm going to use this to find the amount of current that's flowing through here. Now, possibly,
And it's not a 10-volt battery, isn't it? It's a 250-volt battery.
I like 10. The answer is going to turn out to be the same resistance no matter what voltage I use, so I'm going to use something different. They tell you to use a battery of voltage E, so I'm going to use 10.
When you hook up the battery, does it matter what side is positive and what side is negative?
No. Okay? And now what I'm going to do is I'm going to use Kirchoff's laws to get there. Now this is going to be interesting because we're going to end up with some fairly large number of currents, and that's going to intimidate us. And so what we're going to do is to resort to the calculator in order to help us out. So here we go. I'm going to pick a point. I need to start with a point. And I'm going to mark all the currents going into and coming out of that point. Now, because of the way I put the power supply, with the plus side here and the minus side here, I suspect that this current is going to go this way. Like so. Right? These other currents, I don't know. Let me guess that this current here is going to go like that, I2. This current here is going to go like that, I3. And maybe this current I4 will go here, and I5. And oh, look at that. I thought that the other problem, 22, had the largest number of currents. If that one is actually the one that does. I6.
When exactly
How do you?
make it an I2 instead of a continuation of I1?
Great. Good question. The reason that this is not a continuation of I1 is that you have an additional branch coming in.
So if you branch,
Yeah.
it goes 2 and 3.
Yeah, exactly.
Okay.
Because what has to happen is these two have to add up to I1 because they're coming together. Okay.
Why wouldn't this one right here? Oh wait.
Why wouldn't which one would?
Wait.
Talking about I6 right here?
I4. What does that connect to make I5?
That comes into this point right here, and then it splits.
Oh, okay.
Part of it goes to I2, part of it goes to I5.
Really confused.
And now I'm going to pick points in my circuit. Now, a really good question was asked in the other class. How do you know where to pick points? Well, first of all, I'm only going to pick points that have 3 or more wires coming out of them. Because if I pick a point that just has 2 wires coming out of it, then all I discover is that I1 equals I1, which I knew already. So I've got 1, 2, 3, 4 points that have 3 or more wires coming out of them. Everybody see that? And I'm going to create equations for all but one of those points. Since I have 4 points, I'm going to get 3 independent equations out of them. Why not 4? Well, because the fourth one has to be the sum of the other 3 equations. It's dependent on the other 3 equations in order to be consistent. All right, so this is point A, this is point B. Let me call this guy point C right here. And the sum of the currents at point A is going to be equal to. We're going to take I1 as coming out, so it is negative. I2 is going in, and I3 is going in as well. And all of those add up to 0. Notice that this is mathematically saying exactly what I told you, Alexis, and that is that I1 is the combination of I2 and I3. You see that?
Yeah. I'm just confused, like, wouldn't it be easier if it was just that one middle point taken away? Like, if it were, if the
Here?
current, no, not the point, but the whole entire resistor was taken out.
Well, sure, but then it would be a different problem.
Is there a way to merge resistors like that? Like,
You would have to find something series or parallel, and I don't actually see anything series or parallel here. I might be looking at it funny, but I don't see any series or parallel resistors, which is really unfortunate. So Kirchoff is our only hope.
I guess it was a way to make it easier.
Okay, how about the sum of currents at point B? Somebody give that to me.
And we're just ignoring that middle point, correct?
Yes, that's right.
Okay, that's the one that we're.
It's not so much that we're ignoring it, it's that we know already that I'm out of 4 points, I can only get 3 independent equations.
So it's I1 minus I4 minus I6?
I1 minus I4 minus I6. Perfect. And that adds up to 0. And then finally at point C, what do we get?
Minus I, or negative I3,
Mm-hmm.
and then step out.
Okay. And you can see that if I add these together, then these guys cancel, those guys cancel, these guys cancel, and what I get is I2 minus I4 plus I5 equals 0, which is exactly the equation that we would get right here. Minus I2 plus I4 minus I5. So that one times negative 1, basically. Okay. All right, so that's 3 equations. I have 36 variables. I need 3 more equations, which means I need loops. So what loops shall I take?
Like this, like go.
Tell me where to start.
From the. Wait. But,
Triangle ABC. Yeah, that's a loop. So I'm going to start at A, and I'll go around here like so, and that'll be loop number 1. Okay? Now as I go around the loop, again, I'm going to pay attention to current flow. My current is flowing this way, and that means that I'm going to treat that resistor as plus minus. This current is going this way, plus minus. This current's going this way, plus minus. This current's going that way, plus minus.
do you only need one loop?
We're going to need 3 different loops ultimately because we need 3 equations. We have 6 variables.
So if you have the big loop, then you do the small little loops. But
You could have also done this,
don't you have to
or this.
wait, you don't have to do the battery?
You don't have to. No. I think we're going to need to include the battery to get an independent equation at some point though.
Well,
Because if I do just the big loop and the 2 little loops, then all that that's going to tell me is what I knew already, that these currents add up.
what if you do from the battery, from the positive part of the battery, then
Let
just
me do this
run
equation
later?
first, and then I'll come back and take your suggestion. So if I go around loop number 1, then what I have is let's see, I'm going from minus to plus, so I'm gonna add that, 1 times I2. Then I'm going to add plus I4. Then I'm going to subtract minus 5I6. And then I'm going to subtract again minus 3I5. All of that adds to 0. Does everybody see why the signs were the way they were? It's because of the direction that the current is flowing here. As I go around, this is minus to plus, that goes up, minus to plus goes up, plus to minus goes down, plus to minus goes down. Okay. Let me take a loop around, where did you want to go, Alexis? Start at the battery?
Could you go from the battery and then just go from, yeah, and then just cut across?
Cut across.
Could you do that?
I really can.
And just do two.
And so if I take that loop, loop number 2, then what I have is plus 10. And now we have minus, because as I go around this loop, I'm going plus to minus. So minus I1, I4, and then minus I2. And all of that adds up to 0. And I need one more loop. Somebody give me another loop.
Just around the whole outside of it.
Sure, works for me.
So wouldn't that be way, like, a lot of...
I think it'll be okay.
Okay.
As I go around this loop here, I have 1 power supply and two resistors. That's not so bad.
Oh,
Sounds
okay.
Yep.
I didn't
So
see
the-
the...
So they go around here, I have plus, I call that loop 3. Yeah. By the way, you guys made Facebook. You got about 20 likes too.
Wait, what?
Oh, the Teenage Mutant Ninja Turtle.
I think I'm teaching Kirchoff's laws. They think I'm drawing Teenage Mutant Ninja Turtles. Okay, so as I go around here, I get plus 10 volts. Then I get minus 5I6.
Why 5?
Because the resistance is 5, so it's V equals IR. Yeah, this circuit
Oh.
obscured that fact because some of the resistors were 1s. And then minus 3I3.
So wait, shouldn't then the one for the 3... Oh, and be 1... Oh, I did that wrong.
Okay. Now this is awful mathematically. We're done with the physics, yay. But this is awful mathematically because I've got 6 equations in 6 variables, and I'm looking at eliminating that down to 5 equations in 5 variables, and then 4 equations in 4 variables, and then 3 equations in 3 variables. In mathematics, we call this an order n cubed operation. It's actually about 2/3 n cubed is the number of operations required, each operation being a multiplication and an addition. So it would be approximately 216, 6 cubed, times 2/3. That's just going to be terrible.
Why don't we just say,
Yes. So we are going to use the calculator to do all of this for us.
That's not I5, 3I5 for the V1. Is it supposed to be 3I3?
Let me see. So loop V1, 3I3. You are correct. Thank you.
And then same, and yeah, the bottom ones.
Okay. Everybody else check that, make sure everything worked out. I think that's good. Okay, and here's how we're going to do this. First of all, we're going to take our equations just as if we were going to do elimination, and we're going to line up all of our variables on the left side, and we're going to line up all the constants on the right side. We can all do that. Everybody do that at this calculator. Line up your variables underneath each other, and all the constants on the other side.
I have to use the back of the paper.
No, copy it, please.
Yeah. Silly smartphone. Good. Here. Where's that? Yes, it's here. Hopefully you're looking at variables. I hope you're not distracted. If you don't understand, it's because you're just paper out. Paper, I can't use this. Well, you will. But on paper, you're going to line up all your variables and constants on the other side. If you're saying that's easy, then great. Do the easy thing. Minus I4 plus I5 plus I6. Check that one. Okay. I4 minus I2 minus 3I3 minus plus I4 minus 5I6. Equals 0. And then minus I4 minus I2 equals 10. And minus 3 and 3 minus 5 and 6. Equals negative 10. Ha! Wow. Okay, we've got all our equations. Now, if a variable is not represented in an equation, what is its coefficient? Zero. That's right. Makes it invisible. Okay. Here's how we're going to think about this. We're going to take no more than 60 seconds, really, to enter all of this into the calculator. And then we're going to let the calculator tell us what the solution is for I1, I2, I3, I4, and 5, I6. And here's how we're going to do it.
Is that like that matrix thing?
It is exactly this matrix. We're going to think of this as a matrix of coefficients. We'll call that matrix A, times a vector of currents, I. I consists of I1 all the way down through I6. And when we multiply those two together, which is represented by these equations here, what we get is the matrix of voltages that you see right here, which is equal to 0, 0, 0, 0, minus 10, minus 10, just like that. So this equation is the same as this equation. I've just changed the form in which I've written it, right? Normally, by hand, we would solve that equation by substitution or elimination. But it occurs to me that if we knew some way to divide both sides by this matrix, or in linear algebra terms, to multiply both sides by the inverse of this matrix, bam, those would cancel, and I would get the I vector directly. I would immediately solve for I1 through I6. Does that make sense to everybody? Conceptually. Okay. In other words, I'm going to do a multivariable version of dividing both sides by the coefficient. Okay. Now here's how we do it. First of all, I'm going to go through and I'm going to enter the matrix A as the matrix of coefficients for this equation.
One.
Here's how you do it. Pull up the calculator. Like so. And everybody hit second and matrix, and you should get this screen right here. This will let you do three things. It will let you select the names, it will let you do some math with matrices, or it will let you edit the matrices. We're going to start by editing. So go over to edit. We're going to edit matrix A. And because we have 6 equations and 6 variables, we're going to make A a 6 by 6 matrix. And when you do, it gives you the entries right there. Now for the entries in A, we're going to use the coefficients of our variables. The first column will be the coefficients of I1 for each equation. The first row will be the coefficients of my variables for the equation. It turns out it's easiest to do it row by row. So I'm going to go across the first row and do -1, +1, +1, 0, 0, 0. I'm just doing the left-hand side at this time. So I enter -1, enter, +1, +1, 0, 0, 0. And that's my first row.
Calculated much faster than this John is.
Well, because she puts up the
What am I going to do for the next one? 1, 0,
0, -1, -1, 0, -1.
0, -1, that's right. 1, 0, 0. Did you say -1?
Yes.
0, and -1. So you've seen this before. What am I going to do for the next row?
0, 0, -1, 0, 1, 1.
That's it. Okay. It was mad at me. Why? Go down to our third row here. So, tell me those numbers again.
Third equation?
Uh-huh.
0, 0, -1, -1, -1, 0. Unless I copied it wrong. I think I copied it wrong.
Well, I need another number.
The third digit is 0. I mean, I'm sorry, the last digit is 0.
-1.
Oh, I did copy it wrong. No wonder it's good.
That should be 0, 0, -1, 0, 1, 1. Okay, and that's our third one. Now for our fourth row, we're going to have what? 0, 1, -3, 1, 0, -5.
Wait, why do you have negative? Wait.
Now notice that I haven't done anything with the right-hand side yet. That's okay. And then over here, we got what? 0, -1, 0, -1, 0, 0. And then we have 0, 0, -3, 0, 0, -5. That's it. That was the hard part. Yeah, it should, your last column, we'll go over to column 6 here so you can see it.
Just what are they? I can't, my contacts.
Okay, so the last row,
The last two.
the last two. So I'll just read it off here.
I can just put it.
0, -1, 0, -1, 0, 0 is the fifth row. And then the sixth row is 0, 0, -3, 0, 0, -5. Okay? Okay. Well, that's our A matrix, and it took us, I don't know, it took us about 2 minutes to enter it, talking through it, right? In reality, it would take us 60 seconds. It goes real fast. That's the matrix A. Now, we need to enter the constant matrix, the voltage matrix on this side. So we're going to go back to second matrix, and we're going to edit again, but this time we're going to edit matrix B.
5, 6.
Other way, 6 by 1. It's rows, columns.
Gotcha.
It's not X, Y.
Okay, so wait, second matrix, B, edit B of a what?
We're going to make it 6 by 1. 6 rows, 1 column. And that matrix is very simple. It's going to be all of my right-hand side,
And then
which is
-10.
0, 0, 0, 0, -10.
exactly 0, 0, 0, 0, negative 10, negative 10. Kind of
And then do you do math? And
even
then-
easier. So we have entered the whole problem. Now we're going to solve it. Our equation currently looks like this. A times the current vector is equal to B. Therefore, the current vector is equal to the inverse of A times B. And we're going to literally enter that in our calculator like this. Quit out, second quit. And this puts up our screen here. And you're going to go to second matrix, and this time you're going to do names. And if you hit enter, that'll give you A. And if you were to hit enter at this point again, it would simply put A on the screen. We're not going to do that. Instead, we're going to take the inverse of A by using the -1 button. So that's A to the -1. And then we're going to multiply that
How do you
times.
get out of this? Never mind, I'm not gonna get that.
We're going to go back to second matrix, and this time for names, we'll do B. So our screen should look like A inverse times B, literally. Yep, exactly. And when you hit enter, sure, bam, no inverse.
Singular net.
I got it.
Wait, negative 1. Where's the -1?
Well, it's going to take me back to there. A inverse B. Okay,
Oh.
that means that we entered something wrong.
Singular.
What that means is that we have, that these 6 equations are not independent of each other. The singular matrix means these 3 equations are not independent. And so the question is, why might they not be independent? Is it a physics thing, or did I just enter them wrong? So somebody read off the rows to me, just so I can check that we did it right. Here. Row number 1 is?
-1, 1,
1.
0, 0, 0.
No. 1. -1, 1, 1, 0, 0, 0.
That's right.
1, 0, 0, -1, 0, -1.
That's right.
0, 0, -1, 0, 1, 1.
Good.
0, 1, -3, 1, 0, -5.
Yep.
0, -1, 0, -1, 0, 0.
Yeah.
0, 0, -3, 0, 0, -5.
Yep. Okay. So we entered it correctly. That means that maybe my physics is wrong. So let me go back to the previous one. Yep. And we're going to see if our equations were correct to begin with. The first one came from node A. We said I1 going out, I2 going in, I3 going in. That's good. The second one came from node B, and we said I6 going out, I4 going out, I1 coming in. Yep, that's good. The third one came from node C. We have I5 going in, I6 going in, I3 going out. That's the next one came from
The
Circle
loop 1.
loop 1, and that would be loop 1 was this loop right here.
Negative to positive is a drop, you said?
Ah, I think I see what happened. Yes, I do see what happened.
Go from positive to negative, so it dropped.
No, something a little more subtle.
I wrote out wrong.
No? I'll bet we did them all right. I bet we did them all right. But does everybody see this loop 3 right here?
Uh-huh.
Notice that loop 1 goes this way, right? And loop 2 goes this way.
You need one of the opposite?
If you take and combine loops 1 and 2, what do you get? You start here, you go around, skip this because these cancel, you do that. Loop 3 is the same as loops 1 and 2 combined. So of course I ended up with a singular matrix because I only had 5 independent equations. We needed to do a different loop. Instead of this loop 3,
You just do it in reverse.
but no, then we're going to take one of the smaller loops right here.
So B, C.
We're going to make this loop 3 right here. And so when we do, that's gonna change this one equation right here. And when it changes that equation, it'll change the last row in our matrix, and then life will be good.
Okay, wait, which
Okay. So how does this loop 3 go? Well, we're going here to here, this is plus, so this is minus. So we're gonna go up by 1 I5. We're going to go down, then we're going to go up again by I4. And then we're going to go down by 5 I6. And that adds up to 0. And that should be much better. So let's go back and change our last equation to be consistent with that. I4, I5 minus 5 I6.
Wait, can you go back to the other page?
And all of that adds up now to 0. Okay. So if we go back to our matrices, we're going to change the last row here to be 0, 0, 0, 1, 1, and minus 5.
Pardon the interruption, it was a code red false alarm.
Okay. And we're also going to change matrix B to have 0 in the last entry right here. This does not often happen, by the way. It happened here because we had a very large system, and so it was hard to guarantee that we had independent solutions. Okay, and now if we quit out, then we still have this A inverse times B there, and when we compute it, ta-da! Now we get a system of i's. How do we interpret this? What this is telling us is the values of I1 through I6. So I can immediately say that I1 is equal to 6.3 amps,
Yeah.
which is huge. I2 is 4.8, etc. Let me write them all down. I3 is 1.5, I4 is 5.2,
I6 is 1.11111.
what's I5?
0.370.
Okay. All right. So we have these currents here. Now, how does this relate to the question that was asked? It relates in this way. I was supposed to find the resistance between points A and B. Okay. So, since I plugged a battery through here, then the equivalent resistance is going to be the battery's voltage divided by the amount of current going through that battery. And the amount of current going through that battery is I1. So if I take Req to be equal to 10 volts divided by the current that is there, 6.3 amps, and what I get is, hang on one second, is 1.58, 1.59 ohms. And if I compare that to what I was supposed to get, which was 27 over 17, 27 over 17 is 1.58 ohms.
Can you just go back to that? Can you scroll down actually for a second,
Uh-huh.
and then go back to that other page?
Let me stop.